Okay, section 5.4 is over the fundamental theorem of calculus. So what we're going to be doing is we are going to be learning part 1 of the fundamental theorem of calculus because you actually have already learned the second part. The fundamental theorem of calculus comes in 2 parts. The second part is actually just the evaluation theorem that you learned in lesson 5.3. The evaluation theorem, to review, basically just means that if you're taking the antiderivative from a to b, or finding the area under the curve from point A to point B of a function, you antiderive, and then you plug in the value of b and the value of a and subtract the 2, and that gives you your total area. The first part of the fundamental theorem of calculus really has nothing to do with the evaluation theorem. Before I start with that, it says the whole crux of the both parts of the fundamental theorem of calculus is that they connect the 2 main operations of calculus, which are the derivative and the integral. So what we're going to learn here is we're going to learn that functions can represent antiderivatives, just like functions can represent derivatives and second derivatives and what have you. But you can create an entire function out of an integral. So let's start with that. Here's what an example could look like where we are using the first part of the fundamental theorem of calculus. So it says f is the function shown, so that's this graph, and g of x is a different function defined by the antiderivative of f from 0 to x. Find and estimate g of 0, g of 1, all the way through g of 5, then give a rough sketch. Okay, so when I look at this, g of 0, that means that the x value is equal to 0. So I'm going to go to this little equation here, and everywhere that I see an x, I'm going to be putting a 0 in that spot. So I've already got 0 right here. I'm going to write it as everywhere I see an x, I'm putting a 0. Let's make one other quick note again, that this function here is the function f of t. That's this graph. Okay, to find the value of g of 0, we have to work through this side of the equation, which this is just asking what is the area under the curve from x equals 0 to x equals 0. Okay, the area under the curve from 0 to 0 would have to be 0 because you're not moving anywhere. There's no interval to be found, so 0 would be the solution. Okay, let's try this from when x is 1. So again, here's my equation. Everywhere that I see an x, I'm going to put a 1. All right, this time we actually are going to do a little computation. So this one says, find the area under the curve from 0 to 1. So 0 to 1 would be like this space here. And that is the shape of a triangle. So we would just use a simple area of a triangle formula to help us find the area under the curve from 0 to 1. For a triangle, you do base times height. 1/2 that. Base is 1 unit. Height looks like it's 2 units. So this value is going to equal 1. Okay. Let's try g of 2. So for g of 2, everywhere I see it, x, I'm going to put a 2. And so to find g of 2, we need to find the area under the curve from 0 to 2. Well, from 0 to 1, we already know that this area is equal to 1 unit. So we maybe just want to find the area from 1 to 2, and then we can add that to our total. So this is a rectangle. So to find the area from 1 to 2, we would just want to do base times height, which is 2. But we also want to add the area from 0 to 1, which is 1 unit. So this is going to give us a total of 3. Okay. Go, I'll just keep All right, G of 3. Again, everywhere I see an X, I'm going to put a 3. So to find the value for G of 3, I'm going to find the area from 0 to 3. Okay, so let me go back. I already know from 0 to 2, the area is 3. So I want to go a little bit further. So I think I'm just going to find the area of this little blue triangle and add the area that I already had. So for the area, I already had an area of 3. So if we add on this triangle, that would be 1/2. The base of that is 1 and the height of that is 2. So I think that's just adding on another 1 unit, so 4 would be the total for that. Okay, we have 2 more to do, and then we will do the second part of this question. So from 0 to 4, we need to find the area from 0 to 4 to find or compute G of 4. So from 0 to 3, we know it's equal to 4. From 3 to 4, let's see. If I go a little bit further, I have this triangle down here. Now, see how this triangle is underneath the x-axis? Remember, anything under the x-axis is like a negative with your total area. So we're starting with an area of 4, but we're going to subtract the area of this new little triangle, which I think has a base of 1 and a height of 2, just like the others. So we'll be subtracting that total. So that's going to give me 4 minus 1 is 3. Okay, last one, G of 5. Everywhere we see an X, we put a 5, which is basically going to tell us that we need to find the area from 0 to 5. Well, the area from 0 to 4, the net area is 3. We are going to add on, actually subtract, because it's a negative area again, the area of this little triangle. Okay, the area of that little triangle looks like a base of 1 and a height of 2 again, so this is going to give us a total of 2. Okay, the second part of this question says give a rough sketch for G of X. So remember, all of this computation that we were doing was to describe a new function called G. And now, since we have computed all these values, we know something about G, a little bit, not much, but we know that when X is 0, that the Y value is 0. We know that when X is 1, the Y value is 1. So there's a point at 0, 0, and there's a point at 1, 1. There's also a point at 2, 3. There's a point at 3, 4. There's a point at 4, 3. And there's a point at 5, 2. Now, we don't know a whole lot more information about this curve. It could be a nice curve. It could be a rigid line. But we know that these points exist on it. Okay? And all of that information that we just found all came from the definition that G was equal to the antiderivative of this f function here. Okay? Let me show you fundamental theorem of calculus in a little bit more of an abstract way. So, suppose G of X, some function, is equal to the antiderivative from a to x, where a is 1. Okay, so let's make that change. Let's make a into a 1. And f of t is t squared, so that would go here. Okay. Find G prime of X. Well, in order to find G prime of X, we need to know what this side is equal to first. So we're going to compute. Okay, remember to antiderive, you're going to do add 1 to the power, divide by the power. So that would end up being 1/3 t squared, or not t squared, goodness, t to the third. And we are evaluating this from 1 to x. And we can keep going. Let's plug in the x. And let's plug in the 1. and let's solve. So if we solve this, we would get 1/3 x to the third minus 1/3. So that's the equation for the function g of x. Now you're going to use this equation to find the derivative of g. So do your derivative. Multiply by 3, that makes that go away, so that would be x squared. The derivative of a constant is always 0, so it just ends up being x squared. Okay, do you notice anything weird about the answer? Basically, if we take the antiderivative and then turn around and take the derivative, won't we end up with what we started with at the beginning? So basically, the derivative and the antiderivative kind of cancel each other out. The only change that you really can see visually from the very beginning to the very end is that this function inside is no longer t squared, it has become x squared. The reason it has become x is because there's a variable here in the interval that we're using to distinguish and identify the function. So that's just kind of changing it from t's to x's. This guy up here is going to do that for you. The fundamental theorem of calculus, the first part, is just a shortcut telling you that, hey, if you take the derivative of an antiderivative, exactly like what we did up here, you can skip all this middle stuff. You can skip all this because we know a derivative and an antiderivative just cancel one another out, okay? So if I say that g is equal to the antiderivative of some function, then I can say that g prime of x will be equal to this function here, but with whatever this variable is plugged in. So take out the t and replace it with whatever this variable is up top. Okay. One quick thing, I just wanted to show you that it is possible to write things in Leibniz notation. It's just a fancy name given by the guy that, discovered it. But basically, the fundamental theorem of calculus would look like this. It would look like g prime of x is equal to the derivative of the antiderivative, which those are the two things that cancel each other out, which is then just basically the same as the function on the inside with x plugged in instead of t. Okay? So you can decide, how do you want to handle this? Do you want to do this the long way, like we did here? Or do you want to use the fundamental theorem of calculus that allows you to skip a bunch of stuff? The fundamental theorem of calculus says if I want to find g prime of x, I want the derivative of this function, and it's identified as an antiderivative, then all I have to do is recognize that a derivative and an antiderivative cancel each other out, and I would be left with an x inside instead of a t. That is it. Now, it can be a little bit trickier than that if the thing that you are plugging in, like this guy up here. So let's say if you have g prime of x and you're plugging in an x to the fourth, one tiny thing that can make things a little tricky is if that thing you're plugging in is a baby, has a derivative other than 1, I should say. So for this one, I'm plugging something in, and that's creating a mama-baby situation. So because I am doing a derivative, technically speaking, you would also need to account for the derivative of your baby. So this one, you would have to also do an extra step, and that is to multiply by the derivative of your baby. Still, in the grand scheme of things, not that bad. All right, so here are the two parts of the fundamental theorem of calculus. Part 1 is what I just showed you, where you're defining something as an integral function and taking the derivative of it. And then step 2, this is called the valuation theorem. Okay, super, super important stuff right here. The second part to this lesson is where we're going to learn something called the average value of a function. Average value of a function is something where you are analyzing over an interval from A to B. And the average value is basically the average y value that would give you a rectangle the same area as the area tracked under the curve. Okay, so if I said, oh, this area is 10, the average value would give me the height of a rectangle that would make this also an area of 10. Best way to explain it is with an example. So here we go. Find the average value of the function from -1 to 2. So let me start with the basics. To find the average value, AVE means average, you are going to do an antiderivative from -1 to 2 in this case. You're going to do something extra, and the extra part is you're going to do 1 divided by b minus a, which is like the beginning and the ending of the interval. You're going to put that in front of your integral. So that means we're going to take the antiderivative, but there's going to be a 1/3 that we multiply by at the very last step. All right, let's keep working on the math here. So antiderive 1, the antiderivative of 1 is x. The antiderivative of x squared is 1/3 x to the third. And we are plugging in -1 and +2. So we're now applying the evaluation theorem. Let me start with plugging in 2. So I'm going to plug 2 in. Okay, and then we subtract and plug in -1. Okay, kind of messy. Don't give up yet though. We can do this. Okay, so we're just going to work through the simplifying process. So we have 2 plus, this would be 8/3. This would become a +1. And then over here I'd have -1 times 1/3 is -1/3, but then that would make it a positive again. So +1/3. And we end up, I'm going to go back to the parentheses. This would be 3 plus 9/3, which is 9/3 is 3. So 3 plus 3 is actually just 6. So this answer is going to end up being 2. And remember, that is the average value. Okay, so I think it's easiest if I go to a picture and try to explain visually what this means. So here's what the area under the curve from -1 to 2 looks like for the function that we were just analyzing, 1 plus x squared. Okay, the average value tells me that I could make a rectangle with a height of 2. Let me see if I can do this nicely. Since the average value is 2, I can make a rectangle with the height, a height that is equal to 2. And the area of that rectangle is the same as the area under the curve, that purple space. So all of this area is equal to the area under the curve in that purple space. So isn't this kind of a shortcut? Because if I have a picture of a rectangle right here, could you tell me the area under the curve? The area under the curve would be the exact same as the area of this rectangle. Looks like this rectangle is 3 by 2. Which is 6, which that is exactly going to be the same as the area under the curve, the purple space. So kind of interesting stuff. Okay, that is more on average value, or sorry, yes, average value here. This is basically a slide telling you that the average value of a function is kind of like a mean value theorem for integrals. So the theorem says if a function is continuous from A to B, there's at least one number such that the y value is equal to the average value. So basically, if you have a continuous smooth curve like this purple line here, then there will be an average value at least one point on the curve. That's all. Okay, here's how this is going to look to apply that mean value theorem for average value. It says demonstrate the mean value theorem for integrals that there is some number c between -1 and 2 for which f of c equals the average value, blah, blah, blah. Okay, so this is, we're going to say that f of c is equal to the average value, and the average value is 1 over b minus a from a to b of our function. If we plug in what we have for this particular problem, we know that 1 over b minus a was 1/3, and a to b was -1 to 2, and we knew our function was 1 plus x squared. Okay, and because we've already computed this whole value, I'd rather not reinvent the wheel. And we got, I believe, 2 for that, didn't we? Okay, so I told you average value is the y value, right? This is the y value. But what's happening in this problem is you're being asked to find the x coordinate where this y value exists. What x coordinate gives this y value? Well, what you're going to do is you're going to plug in 1 plus x squared for f of c. You can call it 1 plus c squared if you'd like. Doesn't really matter. And you're going to figure out when x is what, or what x value gives me a y value of 2. Okay, so you're just going to solve this like an equation. Subtract the 1, square root, and you get plus or minus 1. However, -1 is in the interval. Actually, I guess both of those would work, wouldn't they? So you get x is equal to +1 or x is equal to -1. Okay, let me go back to the picture and show you what that means. That means that if the average value is 2, that's the y value. When x is -1, the y value on this curve will be equal to the average value. So when x is -1, the y value is equal to 2, and that is the average value that we found when we computed. The same thing goes for when x is equal to +1. The average value is 2. So it's basically just telling you where you can draw your line. From what x value, you can draw your line. Okay, so average value on its own tells you a y coordinate. The mean value theorem for integrals, basically applying mean value theorem to this average value situation, gives you the x coordinate. So this gives you the x value where the average value exists. All right, that is it. You have a Delta Math assignment over 5.4.